Okay, so in this numerical example, that in pulse turbine illustrated in figure number 4, which is this figure here, the fixed nozzle blade give the fluid an absolute velocity v1, which is 600 meter per second. So this is the velocity given, and alpha 1 is also given, which is 30. So v1 is given 600 meter per second, and alpha 1 is given, which is 30 degrees. So this is the angle with the vertical to the tangential direction, and the rotor blade's outlet angle beta 2 is 30. So beta 2 is also given, which is again 30 degrees. The mean blade radius is 0.5 meter, and the turbine rotate at omega, which is 3600 rpm. So you need to calculate the following. Okay, so in part A, determine the tangential blade speed u, it mean radius r, and draw the inlet and outlet velocity diagram. So in this case, you need to calculate u here. So in part A, we need to calculate u, which is obviously r omega. So r is given, which is 0.5, and omega is given, which is 3600. And you need to convert this into radian per second. So you need to multiply by 2 pi by 60. If you just do this calculation here, what you will get is 188.5 meter per second. And now you also need to draw the inlet and outlet velocity diagrams. You need to draw the outlet diagram here and here. So it's the inlet and outlet of the rotor blades here. So to draw the diagram, we know that the U is the same for both inlet and outlet. So we will draw U in this direction here, which is, we just found out, is 188.5, and this is the tangential direction. So in this case, now we want to calculate or we want to draw this vector v1. So v1, and again, you need to satisfy this condition that v is equal to u plus w. So u here is v here is in this direction here. So this is our v1, which is 600 meter per second, and then w is obviously this here. So this is our w. We can see that u plus w is equal to v, but obviously w is unknown here, and this is our angle beta 1. This is angle is alpha 1, which is 30. Okay, so this is the inlet velocity triangle. Now we also want to draw the exit velocity triangle here. So to draw the exit velocity triangle, what we can do is that this is our v2 here, and this is the angle which it make with the tangential directions, which is alpha 2. This is our position 0, this is position 1, and this is position 2 here. Therefore we call this v1, and we call this v2, and this is alpha 2, and this is alpha 1, and this is beta 1. And now we know that the w here, this is our w here. So this w and this w should be the same. The length of these two should be the same. Obviously this is not drawn according to the scale, but this w and this w should be the same. Okay, so in this case, we know that the this angle is given, which is B2 here. So this angle is this angle here. So this is beta 2 is equal to 30 degree here. This angle and this angle is given. Okay, so this was our part A. So you need to draw the diagram and you need to calculate the u here. So in part B is determine the magnitude of the relative velocity of the inlet flow to the rotor blade. To determine the magnitude of the relative velocity of the inlet flow to the rotor blade, so means you need to calculate this W, and obviously you will need to calculate the B1 in the second in part C. So in part B, you need to calculate W. So to calculate W here, what we will do, we will just so if you call this is point A, this point B, and this point C here, we know that this is a right angle triangle. So this W is equal to AB square plus BC square under the root. So from the diagram, you can see that because V1 is given, this angle is given, this U is given. So you can calculate this AB. So AB is actually the 600 cos 30. 6 cos 30 is from if we call this D. So 6 cos 30 is dB, and now you need to subtract U, which is this distance here, to calculate this AB. So minus 188.5, so this square, and plus the BC is this thing here, which even you can calculate from this V1, which is 600 sine of 30, and again this will be squared and under the root. So from here you can calculate W, which is 447 meter per second. So it is just a trigonometry. Now in the part C, you need to determine the blade angle beta 1 at the inlet for the smooth fluid flow. So again, this part C is you need to calculate this beta here. So beta, again, you can calculate beta 1 from this triangle, so which is again tangent inverse BC divided by AB, and we just calculate BC and AB here. So you will just put the values again here, and from here you will get the value of this beta 1, which will be 42.2 degrees. Okay, in part D, you need to determine the magnitude V2 of the absolute fluid velocity at the outlet and its direction alpha 2. Now you need to calculate V2 and alpha 2. Now we know that because in this is impulse turbine, so in impulse turbine, the relative velocity will remain the same. So this means that this W for the inlet should be equal to the W for the outlet. So this means that this W is again 447. So now again from this triangle here, we will try to create a new triangle here. So we will call this point E and this point F. So now you need to calculate this V2, which is part D. So V2 will become equal to uh, dE square plus EF square under the root. So again, you can see that dE, which is this distance here, so which you can say that because W is given, which is 447 cos 30. So 447 cos 30 is this whole AE. So now if you subtract 188, 0.5. This become equal to DE, and then EF is just 447 sine of 30 under the root, and again this is square. So this will give you a value of 299 meter per second. So now we also need to calculate alpha 2. So alpha 2 is again tangent inverse EF divided by ED, and obviously we already calculated EF and ED here, so then you just put the values here and try to calculate this alpha, which will come equal to 48.4 degrees. And finally, if the fluid flow mass flow rate is 20 kilogram per second, so in the part E you are given m dot, which is 20 kilogram per second. What you need to calculate is calculate the power developed. So you need to calculate the power here. So in the theory part, we derived the equation for the power, which was m dot u, and the well velocity, which was v1 cos alpha 1 plus v2 cos alpha 2. So in this case, you just need to put the values here. We know everything. So m dot is 20, u is 188.5, v1 is 600, and angle is 30. So cos 30 plus v2, which is 299, cos 48.4, which we just found out. So from here you can calculate this value, which will become 2.7 10 power 6 watt, or 2.7 megawatt. This is how you will calculate these values here.